Hello, everyone.
Hello, Roger. Hello, Steven. I will connect from other terminal. We should make. You should make Steven. Not Steven. Raju.
Делают люди.
Raju.
А себя сделай. Ты уже зашел, нет? А тебя надо сделать хостом, когда зайдешь.
Hello. Hello.
Okay, good afternoon. We do have a joint group meeting and at a special time. So today's presenter is MD Mazamal Kamal Raju. So he started an interesting project on conductivity in solid electrolytes during the computational chemistry class, and since then he did a noticeable progress that he wants to share. And any feedback and questions are very much appreciated and welcome. So Raju, please do not mind if questions will be sounded like strong. It's only intended to help you.
Yeah.
You should be able to share. Raju, you should be able to share screen. Professor Kilina, your microphone is muted.
I make you as a host. I make Dmitry as a host.
Okay. Thank you.
So, are you able to see my screen, my presentation slide?
Yes.
Yes.
Yeah. The title of my presentation of my paper is a first principles study of lithium-ion mobility in cubic LLGO solid electrolyte at elevated temperature, because we used the temperature more than 750 Kelvin. And these are the authors, and I appreciated the help Dr. Han and Dr. Dimitri throughout the semester, and the support they give me when I was writing the paper. So what is the aim of this project? The aim of this project was basically the main was to observe, and from there we can calculate the activation energy, and from that electrolyte at room temperature. That was the primary goal of this project. Many researchers or many groups, they performed this kind of simulation, but those experiments or those papers were not that much explicit like we did. So we showed explicitly how we can measure the ionic conductivity from the diffusion pathway, and that was the unique and easiest way to find the ionic conductivity. This is the method I followed for this paper. So we observed the migration pathway and calculated the ionic activation energy. From there, the ionic conductivity. And to do so, to find the migration pathway, what we did, we go through the DFT, molecular dynamics. Then we create a movie to observe the pathway, how it diffuses. Does it hop, or does it make a jump from one side to distant side? And here we observe the migration pathway rate, at which time the lithium makes the jump, or it changes its side to another side, its position to another position. And from that rate, we calculated the ionic conductivity, activation energy and ionic conductivity. So
I interrupt?
That already I said, EFT.
Raju?
Hello?
Yeah,
yes.
I think we have problems with the sound. It's really almost impossible to hear. Like my students say it's like you sound like a robot.
Okay.
Low speed internet. Maybe,
I think so.
Maybe we can try disable camera, and if it doesn't help, then I will start showing your slides and you will only speak. Let's first try to just disable your camera and try to say something.
Okay, so let me disable my camera.
Like stop video in the lower left.
Does it clear? Is it clear? No?
For me,
well, now it is better, but not necessarily that it would be.
Okay, and if there will be more problems, our next level backup, someone else like myself will show slides and you will speak. Roger, since we made a break, let's generally plan to ask questions in chat line, but I have a very quick question to two questions to your previous slide.
Previous slide?
Previous slide.
Okay.
So, and some of the audience will may ask the same question to you later. So, why are you using molecular dynamics rather than transition state search? It's question number one. And comment number two, for understanding your problem, you may highlight that the model has a lot of vacancies. Otherwise, it would not work. Would you please briefly address these two things right now?
Dimitri, can you please repeat again, because the sound was not clear.
Okay. So first one, why you are using molecular dynamics rather than transition state search?
Because we are interested to see the movement of the ions. The transition state, I think it's related to interested in electronic properties. We are interested to observe the movement of ions.
Mm-hmm. Okay.
Okay.
Yep. But later on, we should return to this question because reviewer of your paper may ask the same. Okay, please continue.
So for this paper, the methodology we used, these are the important equations that I have used. For the density functional theory, we used the Kohn-Sham density function theory equation. Then for the molecular dynamics, we used Newton's law, and we also used a radial distribution function to observe the distance between ions. And although we use the electronic properties to observe actually the band gap or the absorption spectra, but for this project, already the thing I was telling I just expressed regarding the question about Dr. Dimitri, that we are interested in the movement of ions, not the movement of electrons. So after that, and from that point of view, from the molecular dynamics, we find we observe the time it makes first transition, the first movement, that we took as a rate, that at the point it makes the movement or it changes the position, and using that rate, we calculated the ionic conductivity of our model we used for our study purpose. So you can see the red, our point of interest. The movement of these blue atoms is the main interest of our study. We want to see the movement of these blue atoms. So, and we used 8 PFU, that means per formula unit. That means the original cell, the cubic cell is the formula is Li7, La3, Zr2, and O16. So if I multiply by 8 formula unit, it become lithium 56, lanthanum 24, zirconium 16, and oxygen 96. So how the mobility of the lithium ions. We'll discuss how the lithium ion, how the mobility of the lithium ion is connected with the concentration of the vacancies. We'll discuss later. So let's just see a movie that we have created from our molecular dynamics. So this was I don't know why it's not working. It was working before for 1000 Kelvin. Let's watch the movie for 1500 Kelvin. Sorry, my connection at home is not that much good. So you see, this is the lithium ion. We are tracking the movement of this lithium ion. This will move from this side to this side. And this movie was made for 15 femtoseconds. So you see, it's just started vibrating. So still it is in original position.
Roger?
Yes. Now you see, it just changed its position.
But on my screen, it doesn't show any movie. I don't know, maybe it's different on for other attendees.
I see also Dr. Han said can't see the movie. I think because of the internet connection problem.
Okay, then Raju, let's try. If I will show your slides, okay. Maybe it will be a little quicker.
Yes.
Then please stop sharing and I will start sharing. Do you see anything happening?
Yeah, I see.
Okay, please continue the story and let me know when there will be time for next slide.
Yeah, just run the movie for the 1500 Kelvin. So at the initial time, this is it is in its initial position. So it just started to vibrate. And you see, it just making the transition. So it was for a short period of time, it was in the transition position. Now it moved to its final position. I think you can stop here, Dr. Vijay. Then go to next slide. So as we observed that for all the lithium atoms, this similar phenomena is obvious. So we tried to take a single lithium atom to explain our phenomena. So that's why we took a single lithium atom. So you can see at the left-hand figure, the A, B, C, D, 3D figures. You can see in A, the blue atom, that is the lithium atom is our point of interest. Please let me clear that we didn't show the lanthanum and zirconium atom here. because throughout the movie, and also you will see from the RDF, the lanthanum and zirconium atoms are almost fixed in their position. So we ignored for our clear visualization. So you can see at the very beginning, the 0 Kelvin, the blue atom at its original position. As we increase the temperature at 300 Kelvin in B, so it makes a little movement, but it is still in the original position. It just start to vibrate. And when we increase the temperature to 1000 Kelvin, it hops, it changes its position to the neighboring atom, the neighboring position. And when we further increase the temperature to 1500 Kelvin, you can see it again changes its position to side 3. You can, from the right side figure, you can see at the original position is at A, in which we indicate the position as site 1. Then at 1000 Kelvin, it changes its position to site 2. And when we increase the temperature at 1500 Kelvin, it changes its position to site 3. What is so special about this material? Because this is the dielectric material we want to use for our lithium battery. I don't know the lithium chloride crystal, but it will move through the lithium metals. If we use the two electrode as the anode and cathode, lithium as a metal, and we put the lithium LLZO electrolyte in between, then the lithium ion makes a movement from anode to cathode. That's we can discuss if we have time.
Can I briefly comment?
Yes, when we apply a potential, then from the anode side, the lithium ion makes the transition from the anode to cathode through this LLZO, and this is the electrolyte we used as a dielectric, so that it doesn't make short circuit anode and cathode. But
Roger, please correct me. Is it correct that the main structural feature of this material, which determines this property, is that this material is, so to say, porous, that it has a lot of vacancies, empty spots, yes, where lithium is missing, and therefore lithium ions can move to vacancy?
Yes. Yes.
So it should be declared right at the beginning. It's a very critical, it seems critical point of this material.
Yes, that's why we are interested in this material. That's why the lithium ions from the anode makes the transition to cathode through this material because of the vacancy.
Okay.
This material can have 120 lithium atoms, but we see it has a vacancy, and now it has 56 lithium atoms. Are you clear?
Yep.
So next slide. So from the molecular dynamics, in the movie, we showed that at the initial position, it was at site 1. at 300, 750, still in 750, we increase the temperature to 750 and we see it still retains its original position. It didn't move. So we further increase the temperature and we see that at 1000 Kelvin, it makes a movement from site 1 to site 2. And with further increase at 1500, it makes further movement from site 2 to site 3. Yes, the material is charge neutral. How do you make vacancies of the lithium ions keeping in itself neutral? It's already, the structure is already backend. If we see the chemical structure of this material, it has two structure. IA3D, that means cubic structure, and I41 4D, tetragonal structure. So we are talking about the cubic structure. And for the cubic structure, this material, the lithium ion, it has two sides, or some can say three sides, depending on the position. But for our material we used, there are two sides. There are one tetragonal side and octahedral side. Okay, so the tetragonal side can have 24 electrons, 24 lithium atoms, and the octahedral side can have 96 lithium atoms. So 24 and 96 makes 120 lithium atoms that can be available in this structure. But by default, this solid LLG structure has 56 lithium atoms. So it's already backend position available there. Does it make sense? Yeah, actually, we are not dealing with the tetragonal phase. That's why we are not interested in the phase changing, because we already took the cubic structure. But that's a very good question, because in general, in practical scenario, in reality, at room temperature, you cannot have the cubic phase structure. You always have tetragonal phase structure. So when you increase the temperature around 700 to 800 Kelvin, it made the transition from tetragonal to cubic phase. But for our project, for this experiment, we used cubic structure. Yeah, so far it's neutral. It's stoichiometric neutral, but it is porous because it has vacancy. So next slide. Can you go to previous slide, Dr. Dimitri? Maybe I didn't discuss the right side picture. At the right hand side, you can see the ultimate position of the lithium atom. So at 300 Kelvin, you see 4 oxygen atom is connected to lithium atom. That means it is in tetragonal side. As well, for 750 Kelvin, it is also occupies tetragonal side, but you already seen that when we increase the temperature to 1000 Kelvin, it make a jump and it changes its position to neighboring position. Still, it is in tetragonal side. But when we increase the temperature further to 1500 Kelvin, the ultimate position it regains, it is octahedral side. Because you can see there are 6 atoms. 6 atoms are connected. Actually, there are 8. I don't, because of the picture, you cannot see the other 2. So it occupies the octahedral side at the end of the 15 Kelvin temperature simulation. So from this point of view, we can say the lithium, this lithium atom moves from its original position to neighboring position, okay? And it also moves to the position which is back end. That means whether it is octahedral or tetrahedral, it moves to the position which is back end. So next slide. Yes, yes, maybe I missed some, actually, maybe I didn't explain something in the introduction, what I need to do. That's why it's becoming hard for the audiences to understand. Sorry for that. So if you make a question, then I can make clear if I had missed something. Sorry for that. So from this molecular dynamics, we calculated the distance covered by the lithium ions. So that the displacement that makes by the our observing lithium ion at 300 Kelvin, you can see this is just a vibration. We didn't take this as a displacement. Why? Because we took our unit cell as almost 12.98 angstrom. Okay, so for each cell, the distance is almost 1.3 or something like that. So when we observe the displacement of the lithium atom is more than 1.2 or 1.3 angstrom, then we take it as a displacement, as a movement. So that's why, and also from the movie, it was clear that at the initial position, it was just making the vibration. It was not moving from its original position. So you can see at 300 Kelvin and 750 Kelvin, it doesn't make a move. It just starts to vibrate. But when it is 1000 Kelvin, at you can see at 3500 femtosecond, it makes a jump. At C, you can see at 1000 Kelvin. Okay, and if we further increase, we can see that the jumping time is decreasing. So at 1000 Kelvin, it jumps at 3500, but at 1250, it jumps around 2000 femtosecond. And at 1500 Kelvin, it jumps around 600 femtosecond. And at 1750 Kelvin, it jumps around 1000 femtosecond. So why with the increase, the jumping rate decreases, the time of the jumping decreases. This is because when you increase the temperature, the order geometry becomes disordered. that's why it has more space available to jump. The empty space that available for the lithium ion to make jump. Next slide, please, Dr. Kuruchi. Because I already said that this phenomenon is the similar for all the lithium atoms. So for the sake of simplicity, we just shown for one lithium atom. So all the 56 lithium atom has the similar type of trend. Actually, I don't know why it moves faster at 1500 Kelvin and not at 1750. That's the simulated result we got from our simulation. Yes, the trend is independent of their site. Actually, I read some journals. There was some argument that some group says the lithium ion moves to tetrahedral site more frequently. Some group says it moves to octahedral site more frequently. And some researchers, they said that it moves the position which is vacant, either whether it can be tetrahedral or it can be octahedral. And I may agree with the third group. It moves the position which is vacant to its next position, whether it is tetrahedral or octahedral. So from that molecular dynamics, okay, slide 10, do you see? Actually, Dr. Strom, we didn't see the 4 angstrom movement. Dr. Davis, can you please go to a previous slide? Yes, at 1500 Kelvin, there was a movement around, that is the highest movement I got for the 1500 Kelvin. But when we used the 750 Kelvin, we didn't see that much movement. For more lithium move together. We didn't see that the 2 or more lithium move together, but we can see. But from the movie, we have seen that the place our observable, the lithium ion we are interested in is taking place, is moving to the position where it moves is already vacant because the lithium atom was there, it moved to other position. We can, if we see the movie for the 1000 Kelvin, then it will be a little bit clear for you to observe that when the lithium atom moves to a position its to its neighboring position, it's already backend because the lithium atom was there. It moved to other position. Actually, it doesn't make two or more subsequent jump. It just make a single jump to its neighboring position, and from there it jumps to another neighboring position. It doesn't make the jump at a time, two subsequent jump. It doesn't make the two subsequent jump at a time.
Okay, so what Dimitri said was correct. So from 500 femtoseconds to about 2,000 femtoseconds, it is at a second site. And then from 2,000 to 5,000, it moves to a third site. Is that correct?
Yes.
Okay.
Yes. That's right. Then I can go to next slide.
So I guess one last question on this.
Yes.
And maybe you said this in your intro, but maybe I didn't pick up. In your system, is there only one mobile lithium ion, or is there multiple?
No, only lithium ion is mobile.
Yes, but
only
are there multiple lithium ions that can move?
Yes.
And
all the lithium ion moves in the similar fashion.
Oh, okay. So is this an average, or is this a single one that moves?
We took the average for this single lithium atom.
That doesn't make any sense. How can you take an average of a single?
As for the we calculate the conductivity for different temperature. Then we take the average.
Okay.
So for the different temperature, we see the rate of jump, which I have plotted the Arrhenius plot with the inverse temperature. And from there, we calculated the activation energy for 3 different temperatures. And we extrapolated the room temperature activation energy for this model. And from that activation energy, we calculated the ionic conductivity of our LLGO. And because you can see that 300 for the 1000 Kelvin, it takes around 3.6 picosecond. So from this calculation, we make a calculation from the Arrhenius plot that if we run this simulation for 4 microseconds, maybe we can observe the movement of lithium atoms at 300 Kelvin. Next slide, please. So here we come for the RDF distribution, for the radial function distribution with respect to the lithium atoms we are interested in. You can see the left panel. This is the RDF that shows the distance of all the atoms. That means oxygen, lithium, other lithium, lanthanum and zirconium atoms. And from this picture, you can see the shades are pretty similar because already I said the lithium, the lanthanum and zirconium, they doesn't change they do not change their position. So we see they are fixed in their position. So they make the crystal, solid crystal structure. But when we see the radial distribution function for the lithium atoms, with respect to the lithium atoms we are interested in, we can see with the increase in the temperature, the area under the curve is increases. That means the lithium ions is moving. And also we can make a comment that because of the breaking of the breaking the chain, because of breaking the bond by lithium ion, that's why we get the activation energy, and from there we can calculate the ionic conductivity of the lithium atom. That's how we calculated the conductivity of lithium ion for this sample. Next slide, please. So, so from this project, what we have learned that from the molecular dynamics, we can see how the lithium ion changes its position to another position, from one side to another. And we have seen that whether it is tetragonal side or octahedral side, it makes a jump to its neighboring side, whichever it gets vacancy. And also we can comment that when there are more vacancy, the jump will be more frequent. It will make more jump if it gets more vacancy. So the prime goal of this material, to work with this material, will be to get more scattered lithium arrangement. If we can get more scattered lithium arrangement, then we can make more frequent jump and we can get higher conductivity. But one disadvantage of this simulation is that with the real life scenario, that the loss of lithium and oxygen we didn't consider, that happens due to high temperature. So I have questions, Dr. Khan. Actually, I already told that we just take the observation for a single lithium atom, but this observation can be true for all the 56 lithium atoms. Does it make sense? Okay, so if you see the movie for the 1000 Kelvin, we can see the movie for the 1000 Kelvin, then we can see the other lithium atoms is moving. Then I think it can make some sense. So go to conclusion, Dr. Dimitri, or you can go to movie.
Yes. Which slide is this?
I think in the movie slide, yeah. Actually, the purple one is the lithium atoms. The pink atoms are the lithium atoms. and the red atoms are the oxygen atoms. Because it's we cannot concentrate all the atoms together. That's why I just make the one lithium atom so that it is easy to track. Also, this movie is not clear. You will see this lithium atom will go here and this lithium atom will move, okay? Because if it moves here, if it is not backend, it cannot go here.
Oh, yes, it did move right now.
You see, it moved. It's if you see the movie, then actually this this is the already this kind of experiment has been done, and this is actually universal. You can take as a true that all the lithium ion moves. So maybe not the very similar fashion, the likely same fashion, but in similar fashion, okay? So I think now it is clear. Can you, next slide, please? So I said the main disadvantage of this simulation is that we didn't consider the loss of lithium and oxygen that happens in real life scenario because of high sintering temperature. And also the grain boundary resistance we didn't consider. Next slide, please. Actually, we are not interested in long trajectory. We are interested into fast transition, the fast movement of the fast jump of the lithium ions. That's the time we take for our calculation as a rate. That's why this this project is different than other researchers or other papers. So in that calculation, we can say that with the increase of the temperature, the order geometry get more disordered because of the movement of the lithium ion, and it makes more back-end position for the lithium ion to move on, and that makes the diffusion path to diffuse the lithium ion easily and make it conductive. So if we can make more scattered lithium arrangement, we can have more diffuse lithium ions, and we can have higher conductivity. So from this project, we find the activation energy from the rate, from the diffusion pathway, and from there we find the ionic conductivity, and which is in good agreement with the experimental results published by the other researchers. So one thing I can say that the experiment results has been published by other researchers, it can be different, or there can be a much difference with the experiment results, because the experiment done by the researchers or the groups, they use different approach or different process to synthesize the material. Sometimes they get very good results, sometimes they don't get good results. But we took the value that is pretty acceptable by all the groups. So that is why this calculation, the ionic conductivity calculated from this project, I think is so far in agreement with the experimental results. And that's all for my presentation. So if you have any question, then I can have some answer.
Okay, please join me in thanking Raju for brave and interesting presentation.
Thank you.
So let's scroll through the questions typed in the chat line and give Raju a chance to answer to those of them that were not answered, or if there are emergent questions popped up in verbal way.
Yes, I got a question from Dr. Han that he said that in this case, the focus on the fast lithium. Actually, why we run for the 5 picosecond? Because I said there are a confusion or disagreement that the lithium ion, some says it moves tetrahedral side, some says it moves to octahedral side, and some says it moves to both. So we try to observe which argument is more viable. So we tracked the first lithium atom and we found the signature that it moves both octahedral and tetrahedral side. So we didn't go for other lithium atoms, that's why. So because we got our signature, and this pretty obvious from the picture and the movies that it moves to both tetrahedral and octahedral side, whether it doesn't matter, whenever it gets the vacancy, it moves, it only hops to its neighboring atom, not the far-sighted atom.
If I suggest that you turn on camera while we are chatting for questions and answers.
Yeah, because I'm not sure. Just a minute. Yeah, because I have a problem with the internet connection. That's why I was afraid to turn on the camera.
So let's screen all questions starting from the very beginning, because you were answering some and skipping another. Let's check if nothing is skipped. So there was a question from Yulun at 3:21 p.m. Slide 8. Lithium ions are in various distinct sites. You just show one lithium plus. What happens to other lithium ions?
That's already I said, because it's from the movie we can see, or we can make another, we can observe by taking some other lithium atoms, and we'll observe the same kind of trend. Because this is the paper we're writing, we cannot include all of them. So that's the one, for one lithium atom, we just explain how it moves. And already I said it doesn't matter that it is in tetrahedral or octahedral side, it moves to its neighboring position. When it finds the vacancy, of course, without vacancy, it won't move. That was explicit from our movie.
Then I think then you were answering basically everything. Right now, there are maybe 2 new questions at the end of the chat line. One from Yvonne and another from Levi.
No, because with 10 femtosecond, it didn't move to octahedral side. Am I right? Because we see the movement, it was at the end for the 1500 Kelvin. It was at the end. Okay. You have to see the. Can you go to the presentation, Dr. Dimitri?
Which slide?
The activation, the Arrhenius plot. Yeah, this one, the previous one, the displacement one. Previous slide, Dr. Dimitri. Yeah. So you can see the question was asked by Dr. Levi, that why it moves to 4 angstrom in 1500 Kelvin. So you can see it didn't move to octahedral side until it processed 2000 femtosecond. Okay, so 2 picosecond was necessary for us to observe this movement.
I feel like I have a question. So from what I understand of this would be similar, well, would this be similar in like capturing properties? Well, I'm going to rephrase this. Could this system be used as like a way to capture and hold lithium radicals at a lower temperature, since it seems that the transfer only occurs at a higher temperature, or readily occurs at higher temperature?
Actually, we are doing opposite. What are you saying? We are doing opposite. We don't want to capture or confine the lithium. We want to lithium to move to make more movement. That's how we get higher conductivity, because we want higher conductivity. Whenever the conductivity is higher, then the battery can give you more support.
Okay.
Okay. And one more question from Dr. Levi, that would it the direction? The direction actually it moves in 3-dimensional direction. So the direction generally for this our simulation has no impact, but it generally in real life it moves from anode to cathode, from 2 electrode, from one electrode to another electrode. When you give a potential, and it moves from one electrode to another electrode.
I guess my question is, are you able to see that, or could you simulate like directionality? Because that is incredibly important for these situations.
For this simulation, no. But if we can do it, it would be great. Thank you for this suggestion. Because
I thought that in VASP you can have a electrostatic potential.
Yes, actually, if you remember, Dr. Dimitri, we wanted to use that electrostatic potential, but it didn't work. Am I right?
It does work, but it will be too much for the project.
Yeah.
Okay. So this is to understand the system at a fundamental level, and later you may continue to play.
Explore more. Yes.
So all you're really looking for is, does temperature impact the speed at which the lithium ion can jump?
Yes.
And that's all you care about.
Yes.
And that's the main reason why you only look at the first jump and you don't look at jumps afterwards.
Afterward, yes.
So I know that I just had that conclusion, but while I think it was you, Loon, and you pulled up the slide 10, I think it was, and I think it's temperature 1250, the pink one. It appeared that your ion jumped to one site and then almost instantly it jumped back. And it did a back and forth. It didn't stay in the other site. Is that an issue? Or since you're trying to have your ions be mobile through the entire system, getting stuck in one well has no impact on your results?
Dr. Dimitri, can you please show the slide?
Sure, absolutely.
To Dr. Levi, which one?
Oh, I guess it's magenta. Yes. So, like, there's only from about 2001 to like 2004 that it jumped, and then it jumps back to the original site, and then later on it halfway jumps, and then it goes back, and then jumps again and falls back. Is that an issue?
Actually, this is not the position. It's not indicating. It's just a displacement.
So that is related to position.
It's not the direction actually.
I'm not saying direction. I'm saying is jumping to the other site.
Yes, yes.
And then it comes back, and then it jumps and comes back. So is the non-sticking, so like if you looked at 1500, it does one jump, it stays there for 1500 femtoseconds, and then at 2000 femtoseconds, it jumps again, and it stays in that position for 3000 femtoseconds.
Yes.
Can I add a comment?
Yes.
I'm not sure, Raju, please correct me. It can be a wrong comment, but if we are thinking on about the figure, about the picture of overcoming the activation barrier, the one that activation energy, then if system has sufficient kinetic energy to cross it one way, it may have sufficient energy to go backwards. So as soon as we overcome barrier, we are not looking for directionality of reaction. We're looking for enough energy to be mobile.
Okay. So,
but
I need an approval from Raju. He may.
No, it's absolutely right, because it can move. Because already I said to a question that Dr. Levi asked me, that it can move any direction, and so it can move back and forth too.
Okay, so in the rare case of 1250 Kelvin, it is a endothermic process, where it appears for the other cases is exothermic. Is that
yes, we can say that in general terms.
Okay. So there's no issue that the end result is higher in energy versus the initial point?
No, Dr. Levi, because we are only concerned about the movement. If it makes the movement, then it's good for our system, because as I said, whenever it moves, make a movement, it increases the conductivity, because the more lithium ion move, that the more lithium ion will reach from anode to cathode.
I do have Professor Klina, please unmute your microphone.
Yeah.
It's still muted.
I think.
Oh, no.
I can hear you.
You can hear me?
Yes.
Okay. So just looking on this picture, which is showing on the slide, and dealing with a question from Levi a little bit. First jump of lithium in time. So it looks like you have small displacement and then suddenly a very significant displacement, which again changed by a little bit after some time at higher temperature, when your temperature is 1500.
So you're looking on slide 10?
No, I'm on a slide which is just showing right now.
Actually, yes. Yes.
I mean, it's the same probably information as in the slide.
Oh, okay, the bottom right picture.
Yes, Dr. Klina, this is the picture actually I updated. This is the sudden straight line, because Dr. Dimitri, can you go to slide number 6? 8.
Well, my question is not why this very sharp change is happening. My question was like, this sharp change is happening when you increase temperature. But for 750, we don't see this sharp change.
Yeah, because at 750,
growing with the temperature, why you have in a high range of temperatures not such a significant change in the displacement of lithium. Do you have any explanation?
Yes, because at low temperature, the lithium ion don't have that much sufficient kinetic energy to change its position, to break the bond.
No, but my question is, you have 1000. You switch to another slide, so I don't.
Good.
I think there was like something like 1000, right? Yeah. So the black line is 1500. Then you have 750, the green line, and then the blue one is 1000, right?
Yes.
Okay, so green one is smaller than blue one. That's why green one still doesn't show the change.
Yeah, at 300 and 750, there is no change of position.
Not really a big difference between 300 and 750 kelvins, because it sounds like it's a huge difference in the temperature between normal and when you go to 750 kelvins, right? It's already a constant temperature of metal, I guess, of some metals.
But this is a solid electrolyte. So this is solid. So in reality, when we synthesize this material, we make the pellets of the electrolyte at 1250 Kelvin. 1250 centigrade. That means it's almost 1520 Kelvin. But still, it is in solid. So it is solid crystal.
Okay, even at such high temperatures, it still represent as a solid, not as a liquid.
No, solid.
I see. Okay, and that's why 750 is not high enough, but at 1000.
Yeah. Also, there is another nice thing to say, that I already said it has two phases, tetragonal phase and cubic phase. at low temperature, below 700 Kelvin or 800 Kelvin, it is in tetragonal phase. So in tetragonal phase, it is reluctant to, the lithium ions are reluctant to change its position. It so far firm in its position, but below, above this temperature, it converts to cubic structure, cubic phase. From that point of view, it is more inclined to change its position.
Okay, yeah, so you have a perfect explanation of these trends. Thank you.
Thank you. Thank you for the question.
So I know I'm going to butcher your name, but is it Rajesh?
Raju.
Okay. So Dimitri sent a question on the chat, and he's like asking me would I comment on transition state search versus your method and the pros and cons of transition state. So if we look at the activation energy, the plot right above it where it says initial activation energy, activated complex, and then final state. If we think about transition state, the activated complex is actually the transition state. So there are methods to find that transition state, and typically it's a saddle point. And I'm assuming you know what a saddle point is.
My background is not chemistry, and
have you not taken math? I thought you were an electrical engineer.
Yes.
So like Calc 3, when you talk about like multivariate calculus, and you talk about like a saddle point.
Yes, saddle point.
Okay, so like if you consider the activated complex your saddle point, there's only one minimum energy pathway through that, right? So it would be along the direction of the upside down imaginary frequency, right? So there are some pros to doing this. If you have a relatively simple system, the number of degrees of freedom can be easily scanned through to get that transition state. In your case, I think there's somewhat of difficulty, which is kind of the con for you, where you are not necessarily sure which site your lithium should migrate to in your final stage or your product, right? So to do transition state calculations, you have to know your initial state and any intermediate states that you will encounter, and then your final state. So that is somewhat of a difficulty, which in your case, you got around that by saying, this is my initial case.
Yes.
I'm then going to run several different temperatures and see where the system will go. And hopefully we will find a lower electronic configuration. And when I say lower electronic configuration, you may have more kinetic energy, right? Because like if you're going up your barrier and then you turn down, you're going to heat up, but you could go down in the pure electronic term. So like if you solve the Kansham equation for just the electronic terms, then you could find your final state. Does that make sense, or did I lose you?
No, it makes sense, but it's I have to study about this.
Yes.
I have to make some study about this procedure.
Raju, please listen carefully to Levi, because there is a very high chance that this question will be asked to you by a reviewer. Especially for reviewers of chemical background, it is first and most natural question: why one is doing molecular dynamics instead of transition state search?
Yes.
So,
and
you may want to spend time learning what it is, at least verbally, for comparison.
Yes.
So to do transition state search or to find the transition state, like there's another program called Gaussian, and they do like interpolation. So they take the geometries and they do a linear change from one to the other to get like an initial guess. And then they use the variational principle. No, they do ionic steps until you go uphill to a point that's stable. Alternatively, and I know that this is encoded into VASP, which I'm assuming is what you did. There's a notched elastic band, which could do very similar things that you're actually doing. Now there is complications with NEB because you virtually say, I'm going to take a rubber band and cut it so it's a string, make knots in it, and you then have forces between each knot, right? So like if you think your rubber band, you have the two knots and you pull on them, then you have the force of the spring of the rubber band, and that is one force. And then you also have the second force, which is the potential energy surface from the electronic contribution. So in NEB, you try and minimize the forces, which does not necessarily mean you're at the minimum energy pathway. It just means that you're to pull your atoms where they need to go, or that spring and the potential energy surface are as low as possible. And when you do this methodology, let's say you have 10 different images, you have to do DFT at every image. And you have to do this self-consistently until you get a solution that has the minimum energy. So here you may have done 5,000 calculations, single point calculations, where in NEB, you may run the exact same number of points or even more because of the compound nature of that. So in your case, it may seem like you ran a ton of calculations, but in reality, it could have saved you time doing it this way. Does that kind of make sense, or did I totally go off the rails and lose everybody?
Yes, I understand. What you're saying to, if I do it on bus, so to do the SCF, self-consistent, to see the optimal position, if I'm...
Yes, I'm just looking for a piece of paper. So you keep explaining what you think I said. Actually, I can just Google. Svetlana, am I also...
I think there is another question from...
okay, answer that. And then if... Yes.
Oh yeah, there is a question from...
Dr. Javed. Yeah, I think for this simulation, actually we didn't put any potential. That the question Dr. Levi said, we didn't apply any electrostatic potential.
Levi, are you going to share the link to a website?
Oh, I was going to try and share my screen.
Okay. Oh, just a second. We need to set up you co-host.
Did you answer Jabed's question?
Yes.
Okay.
And there are, Levi, there are two of you. Which one is?
The one that has the mic and video turned on.
Just change the settings as a host. You can change the.
Yes, I did. Both Levi's are now co-hosts.
Okay. So
you don't need to make him as a co-host. Just allow to share it.
Yes. So I just Googled notched elastic band. And this is pretty much what you're asking, right? So you're saying, I have one site, I want to put it in the other site, right? And then find the potential energy surface. You can do it in a bigger system. And this is kind of a very brief overview. So what you do is you do a linear interpolation, meaning you just linearly change your positions with an integer, and you initially get this point. And you have to compute the parallel, which is, I think, the spring force, and then this perpendicular force, which is the potential energy surface. And you have to compute it at every one of these points. And then you have to update your potential, and then you move somewhere along here. And you have to do that iteratively until you obtain your final position. Now, this may seem relatively easy, but you would have to do several hundred or even thousands of calculations to be able to obtain this. And all you really care about is still just this energy here. So someone may ask you about this, or if you look into why this method could work or not work, you could then preemptively say, oh, we thought about doing either looking for the transition state and then being able to use just the energy difference into Ehrenfest equation, or using this. So it may be more info than you can take in, but it's a start to think about how to react to the reviewers. Does that make sense?
Yes, I understand.
Okay.
Thank you for the suggestion.
Yes. But don't try and run this, because it will eat up your time like that.
So it's not a by now it's not a plan for immediate action. It's more like for abstract intellectual comments, potential questions of reviewers. Let's check if there are more questions, either typed or verbal. So
I don't see any new question.
If there are no questions, I would like to invite everyone to join me in thanking Raju and all participants of the discussion. And
thank you very much.
Thank you, Raju. If there are any comments by Professor Kivina, it's time for the regular group meeting. Please go ahead, because for our part we are done.
Okay. No, I don't think it's maybe a few minutes since we have Levi. If Levi is not running anywhere in a couple of minutes, then.
Oh no! Today there's no volleyball.
You're not disappearing just in the moment. Stephen, what are your success with rest of the molecules for getting this corrected spectra? If you want, you can share the screen.
So I think The problem that I'm running into right now has to do with the fact that the two that aren't working have iodine on it.
But can you show the successful spectra first?
The one successful spectra, yes. I've been troubleshooting others, so I haven't had time to clean it up.